Hello everybody. In this lecture I will talk about the hydrostatic forces on inclined surfaces and also hydrostatic forces on curved surfaces. Okay, so before I actually start deriving those relationships and do a couple of examples, I just want to point something out from the last lecture that I gave on the hydrostatic forces on the vertical surfaces, and I just wanted to show you one expression. If you remember the last example that we did, we have this gauge pressure on the top. So once you have the gauge pressure on the top and then you have the hydrostatic pressure, so with respect to this point I showed you the moments. So the idea was, so we took the moment, so F of R is Y of R is equals to P gauge times the area times Y of C plus rho G I XXC plus YC square A. So now the idea is we actually found out where this resultant force was acting. We know where this Y of C is this hydrostatic, or like the gauge pressure is acting, which is at the centroid. But what about this hydrostatic force? Where is that force acting? And we do know that this will be the centroid of this triangle in this case, but I just want to write it in another form. And in fact we did look at it when we looked at the problem when we didn't have the gauge pressure, but so everything else stays the same. So P gauge A times YC plus rho G, and this time what I'm going to do, I actually will divide and multiply. Okay, so I XXC, and this is just to bring that in the form that we are familiar with. So I'm gonna divide this thing, divide and multiply by YCA. So we have YCA plus this gives you YC, and then this quantity is rho G YCA IXXC YCA plus YC, and this is the rho GYC, which was our FR2 times and this is our YR2. So if you remember, this is how we define this. This is the second moment of area about the centroid, and then we had this is the distance from the centroid. So we did look at it, but I just wanted to point out that even though we are writing this expression in this form, but this is equivalent to this. Alright, so let me get back to the hydrostatic forces on the inclined surfaces. So now in this case, so for an inclined surface, alright, so we have a problem where we have this fluid and this thing is making an angle of theta, and you want to find the forces on a gate which is placed somewhere over here. Okay, so again the gate can be of any shape right now, so I just take a random shape, and somewhere over here we have the centroid, and down below the centroid we have the center of pressure. Okay, so center of pressure, where this resultant force actually will be acting. And the idea now with this is the force, because the fluid exerts the pressure in all directions equally, so your force will be acting somewhere over here, which actually will be the point of center of pressure. But at the same time, now I'm going to choose a different coordinate system. So let's suppose if I choose this Y and this as my X, so the resultant force, so let's try to find that out, which is PdA, and I can write this as the hydrostatic forces. Of course this is fluid, so hydrostatic forces will still vary the same way. So this quantity will be rho G and we have dA, and I'm going to put the integral sign. But this quantity, if you remember, this was the height okay, so height, how deep the fluid is. But in this case, as we have shifted our coordinate system, so if this is our y, so y sine theta will basically give me that vertical distance. So y sine theta gives me this distance over here. Okay, so this is y sine theta, so I can write this as y sine theta, and I can take this rho and g out, and especially sine theta, because all of these quantities are constant, and I can write this as y dA. So once I have y dA, this basically is equals to, as I mentioned to you earlier, this is the first area moment. So y dA is equals to yCA. So I can write this as rho g sine theta yCA, which is f of r, and I can call this quantity yc sine of theta. So again, this is the distance, so yc is that distance up till centroid. So this is our yc, and then yc sine of theta is basically this vertical distance. Okay, so let's suppose if this is our centroid, so up till this point I'm calling this hc. So hc is basically equals to yc sine theta, so I can write this as rho g hca. So this is the resultant force, and that's the magnitude. We don't have the location where this force will be acting, but at least we have the magnitude of that force. Alright, another thing, I'm gonna define this point as O, because I'm gonna take the moment of this force, which is f of r, about this point, and then we will try to figure out where this force is acting. Okay, so I'm gonna take the moment about O, and let me just remind you that this is where the O is, and our f of r is acting this way, and this is the magnitude of that force. So f of r is this, and that's where the O is, and f of r is here. So now I'm gonna define this as y of r, f of r is equals to y times rho g y sine theta times dA. Okay, so as we defined our distance, okay, so in this direction we are trying to find the moment. So if the force is acting this way, which has the magnitude of sine theta, so y sine theta, and then you are trying to find, you're multiplying this with this y over here to figure that out, what this moment would be at distance y. So this quantity rho g sine theta basically comes out, because all of these are constant, and then we are left with y squared dA, and then this is y of r, f of r, and as you will notice, this quantity, this is second moment of area. Okay, so second moment of area. So now I have y of r, f of r is equals to rho g sine theta, and this quantity over here is ixx0, because we are taking the moment about the point O. And at the same time, I can write this f of r as, so y of r times rho g sine theta yc times a. So that is the force, which is f of r is equals to rho g sine theta. I'm going to be using the parallel axis theorem. So using the parallel axis theorem, okay, so using the parallel axis theorem, what we have is ixx0 is equals to ixxc plus yc square a. Okay, so those are the two quantities. So I'm going to replace it with ixxc plus yc square a, and now I'm gonna find where the location of that force would be. So just simply divide this by sine theta ixxc plus yc square a divided by rho g sine theta yca. So theta, I mean this cancels out, and what we are left with is y of r is equals to ixxc over yca plus yc. So this is where the resultant force would be acting. And if I go back to the drawing over here, so we had this y of c up till this point, which is a centroid, but now we have this additional term, so y of c plus ixxc plus yca. So that distance will be somewhere over here, so that will be our y of r, okay, which is actually longer than the centroid by itself. Okay, so that's the derivation, and let's actually take a look at an example. Okay, so let's take a look at an example. And okay, so the example says as follows. Okay, so 4-meter diameter circular gate is located in inclined wall. The gate is mounted on a shaft along its horizontal diameter. So the idea is that you have a circular gate of a 4-meter diameter, and it's being mounted on this shaft, which will be able to rotate this way. But then again, you have a stop here. So because you have a fluid, so which is trying to push it this way, and that's why you need to have a stop. Otherwise, you have a higher force here, you have a lower force here, so this thing will try to rotate it this way. So that's why there is a stop here. And what we want to find is the magnitude and the location of the resultant force. So somewhere over here we will have the resultant force and the moment that would be applied to the shaft to open the gate. So if I want to open this gate, we have this moment, I mean the force acting in this direction. So the only way I can open this gate is to basically apply a moment in this direction so that the gate opens, and then we have some flow of water. Okay, so some of the quantities that are given, we are given the angle 60. I am choosing this as my coordinate system along the inclined plane, and so we also know the vertical distance, which is hc. And if you recall from the derivation, this hc is equals to, so I mean we have this yc, so hc is equals to yc sine of theta. Okay, so I can define this relationship, and if I want to find my yc, that will simply be hc over sine theta. So that will give me the centroid distance of this geometry in this coordinate system. Alright, so the first thing is the magnitude. So we can find the magnitude of this force, which I'm calling as the f of r. So f of r is simply equals to gamma times hc a. I mean this is one expression. I can also write this as gamma times yc sine theta a, which actually is the same thing. Or I can also write this as rho g yc sine theta a. Okay, so all of these quantities are the same. And by the way, I'm using this, I mean, so this is a water over here, so I can use the density for the water. So when I multiply all of these together, so 10 raised to power 3 Newton meter cube times yc sine theta, which is hc, and that is given as 10 meters, times the cross-sectional area, which is pi d square by 4. So basically that is 4 pi meters square. So when I multiply all of these together, it gives me 1.23 mega. Okay, so I can write, so 1.23 mega newtons. or into 10 raised to power 6 newtons. Okay, so that much force will be exerted in this direction. Okay, so we have the resultant force, but I don't know the location of that force at this point. But let me just, because we have this quantity, so I can find the centroid distance. So yc is simply, so this distance yc is equals to hc over sine of theta. So we have hc, which is 10 divided by sine of 60. So when I do this, this actually gives me 11.55 meter. So that is our the centroidal distance from here, and I'm also calling this point as O. So with respect to point O, yc is 11.55. So we have the resultant force. So now let's look at where this resultant force would be acting. So I'm going to define this with y of r, and Ixc divided by yca plus yc, and this is the relationship we derived. So this will give us the resultant force. This is the second moment of area from the centroid, and then this is the distance from the O to that the centroid of this shaft, or like this disk. So Ixc for a circular shaft is basically pi r4 divided by 4. So we can find that quantity. So this is basically equals to pi over 4 times 2 meters to the 4 divided by actually that should be 11.55 meters times you have 4 pi meters squared plus yc is 11.55 meters. When you add them up, you basically have 11.6 meters. Okay, so you 11.6 meters, which is yr. So that distance, so going back to our drawing over here, so now you have from this location to the centroid you have 11.55. So again, starting out from here, 11.6. so somewhere over here, that's where your f of r is acting. So on this line your f of r is acting, so that is given by this y of r. So if you want to find it in terms of height, you just have to multiply or divide that by the in this case you have to multiply that with the y of r to basically get the vertical height, but we are only concerned with the y of r in this direction. Okay, so once we have this, okay, so the next thing we want to find is to the moment that would be applied to the shaft to open the gate. So we have to find the moment to be applied to shaft to open the gate. Okay, so for this one I'm going to take the moment. So again, if I have this thing over here, so I will take the moment. So I can also take a look at it from this side also. So we have this force acting in this direction. We have this distance, which is 11.55. we also have another distance slightly more than that, which is actually 11.6 meters. Okay, so I can take the moment, which is about point C, which I am calling this. So take moment about point C, okay, which actually is this one. So I have f of r that's being multiplied with you have this force, so you have one distance, so the difference of the two, which actually will be so f of r times y of r minus y of c. So in this case that is 1 point, so the force is 1.2 3 into 10 raised to power 6 newtons times yr minus yc, even though I'm writing this as 11.6, but once you get that number, this actually is 0.0866 meters. Okay, so the difference of the two would actually be 0.0866 meters, and when you multiply these two, you basically get 1.07 into 10 raised to power 5 Newton meter. So this much of a torque, or the moment, you need to apply at the shaft to basically open this up so that the water can flow out. Alright, so this is for the forces acting on the inclined surfaces. So let's continue with this idea. If you have forces acting on curved surfaces. Alright, so let's just take a okay, so let's just take something like this. So if this is an object and then you have a curved surface and then it goes all the way up till here, again this is a straight line. So this thing is completely filled with some liquid. So what I'm going to do now, I will just separate this curved surface out from here. So if this is the curved surface, and in fact I'm just more concerned with the fluid in there, so this will be the fluid. Okay, and then you have some force acting on top of this. Okay, so the idea is there is some fluid on top of this. Alright, so there's the fluid, and that it has some weight, so that weight is actually acting somewhere over here, so around, so half of this line, so that's where the weight of this fluid will be acting, and I can, which is simply rho g h times the area. So that will be the weight of the fluid that is sitting on top of it, and then at the same time this fluid has its own weight, so that will be acting at the centroid. So if this is the centroid of this this shape, the weight of this will be acting somewhere over here. So you have W1 and then you have W2, which is the weight of this one, and at the same time you have as you will notice that you have so much fluid on the top. So this is the weight where it's acting, then you have the fluid weight, but at the same time you have this hydrostatic forces which being developed over here. So now you have this pressure or this force acting in this direction, so which I am representing by f of h. So this is the horizontal force, so f of h will be acting in this direction. So we do know this f of h is acting in this direction. We don't know the location of that force. And how do you actually so first of all, what that force would be, so the horizontal force is equals to gamma hc times a. So again it will be height hc, okay, and so this height hc times the area times the gamma. And just to mention that this hc, if you look at this object over here, this fluid, so let me in fact draw the same thing over here now. This has some width. Okay, so anytime you have an object, it will have some width. Okay, and this is not the best of the pictures, but the idea is, if you think about this element over here, so this fluid actually, once you think about it, this has some width, and this shape is a rectangular shape, and we are looking at the centroid of this shape. So that's the distance from the centroid to the top of the fluid layer. So this is where the fluid is starting. So this distance is our HC. So that is the distance you need to put in here to find your horizontal force. Alright, so this is what you will be using, and in a similar way, when you are computing for your resultant force where that force is acting, so in that case you will have to use F of H times Y of R, or like where this resultant force is acting, is equals to in this case it should be equals to, I mean you can write it as PdA times Y, and then Y is equals to Y rho G, so Y rho G V, okay, so that's another Y here, and then you have D. Okay, so this implies that rho G Y square dA is equals to FH YR, and this is the second moment of area. So in a similar way what we have done before, what I have showed you guys before, you can find the resultant force is equals to IXXC plus YCA plus YC. So that will tell you where that horizontal force acting on this object. Okay, so that's where this force is acting with respect to some place on the top. So that's where the horizontal force would be acting. The vertical forces, one is halfway in middle, so whatever, if this is your L, so this distance will be L over 2, and that is the centroid. Okay, and then this is also the weight of the fluid, which is simply gamma times V, and then you have some weight of the fluid from the top also. Okay, so the total force, so F total, because you have a horizontal force and you have two vertical forces, one here, one here, so the total force would actually be F H square plus F V square. So that will give you the total force, the magnitude of the total force, and where that force will be acting, it will be tangent inverse times FV over FH. So you have a horizontal force acting this way, you have some vertical forces acting this way, so the resultant will be it might or might not, but it will pass somewhere over here. So this will be given by this angle theta. So you can basically compute that theta, and you have the magnitude for the total force. Alright, so let's take a look at a quick example for this one, for a curved surface. Okay, so the example is a quarter circle gate is hinged at C. Find horizontal force P required to hold the gate stationary. The width of the gate is 3 meters. So as you will notice, this thing is completely filled with the fluid, with water. In fact, I should say water, and this is where the hinge is, C. And if there's no force being applied, this water will actually it will lower this gate down and it will flow this way. So we have to apply some force so that we can counter the force that's being exerted by this water. Okay, so I'm gonna again, there is no force from the top. The atmospheric pressure will be balanced on this side, but if you have some weight on the top, you have to include that. But in this case, there is no water above it, so we will only have to worry about the water of this section. Okay, so I'm gonna take this thing out. So in fact, let me draw it here. So if this is the section, and this has a width of 3. Okay, so I'm gonna define this as something like that. So okay, so that's what the fluid looks like, and this is the cross-sectional area that I am concerned with, because as I mentioned, the horizontal force requires this distance from the top to the centroid. So the centroid, if I look at from this side, this shape will have a width of 3. So the width is 3, and then the height of this is 2. So somewhere in the middle we will have this y of c, which actually is, so half of it, so y of c is 1. So if I am looking at the horizontal force, so the horizontal force is simply gamma at c times a, so which is actually equals to, so gamma in this case I am taking that to be 9790 Newton per meter cube times 1 meter, which is hc, times the 6 meter square, which is the cross-sectional area of that fluid element. And I mean, the way we are deriving this, you can look at the derivation from today's the video, or the last video that I talked about for a vertical, the forces on the vertical plate. Okay, so when I multiply all of these together, it gives me 58740 newtons. So this is the force that's being applied in this direction. We don't know the location of that force yet, but we do know the magnitude of that. The way we can find the where this force is acting, I will use this relationship y of r, which is Ixc over yca plus yc, and we have this yc, which is 1. So yc, the area is 3 times 2. The only missing quantity is this Ixc, so that I can find out by, so which is 1 over 12 b cube times 2 to the power third. And when I mean, so this is the second moment of area for a shape that looks something like this. So when I put all of these things together, so it gives me 4 by 12 plus 1, so which is 1 by 3 plus 1, and all of this is 4 by 3, which is 1.33 meters. So the force will be acting, so again if I take it out like this, so force will be acting, and this is 2 meters, so force will be acting at a distance of 1.33 meters from the top. Okay, so that's what this quantity represents, 1.33 meters from the top. So that's where the horizontal force is acting. Okay, so this is for the horizontal force, and now we also have a vertical force which is acting in this direction. So first of all, we have to find out what that vertical force would be. So to calculate that vertical force, which is simply the weight of the water, is gamma times the volume. So gamma in this case is 9790 Newton per meter cube, and the volume of this is, because it's a quarter of a, I mean if I think about it, is the cross-sectional area times the length, which gives me the volume. So I mean this is a cylinder, so I can find out pi r square, which is like the radius is this r, and then this is your length, or the width in this case, so pi r square L, and I have to divide this by 4 because we only have like the fourth of that, so that's why I have to divide it by 4. So that will in fact be 1 over 4 pi r square, where r is actually in this case r is 2 square times 3, where 3 is the width. So when I multiply all of this, it gives me a weight of 92280 newtons. So once I have this weight, and this weight is acting at the centroid of this of the fluid. Okay, centroid of the fluid geometry, I should say. Okay, so if I look at this, the geometry looks something like this. Alright, so that's what our geometry is. And the centroid is this point here, and the distance from here to here is 4 r by 3 pi. Okay, so that's this distance. So I can compute that, and in fact this comes out to be 0.848 meters. So I do know where this weight force is acting, and we also have where this horizontal force is acting. So we can take the moment, about C, which is this point over here. So this is our hinge. So we're going to take the moment about this C, and we have to find what this force P would be, the required force P. So the clockwise I will take as negative moments, and the counterclockwise I will take the positive. So the first one is a negative because it's trying to rotate it clockwise, so it's going to be minus P times the distance, which actually in this case is 2 meters, and the next force is which is this, it's trying to rotate it counterclockwise, so it is 92280 times 0.848 meters. And then this force, this is also trying to rotate counterclockwise, so plus 58740, and this is acting at 2/3, and that is equals to 0. So if you're taking about the moments, and if you want to balance this out, so the summation of all the moments have to be equal to 0. So 2p is equals to 31960 plus 78253, and then p is simply 58.7 kilonewtons. So this much of a force you need to apply to keep this thing so that the water does not move this plate and flow over. So that's the amount of force you would need to apply. Alright, so that's pretty much what I wanted to cover for hydrostatic forces, and in the next video I will talk about the buoyancy, and then we will look at the stability. See you guys.